right. So my name is Zach Shwirep-Conti, and I'm a research associate at the Alan Turing Institute here in London. And I would also like to introduce the co-host and co-organizer of the seminar series, Andrea Pizzaferato, who is currently ex-former assistant professor of the University of Bath. And for those of you who are not familiar with the Alan Turing Institute, this is UK's National Institute for Data Science and AI. Also, for the benefit of those joining us for the very first time, I'd just like to briefly introduce the topic of the seminar series, that is physics-enhanced machine learning, or physics and for machine learning. Maybe at one point we should debate what this should be called, really. Here, the focus is on engineering applications. As you all might know, physics-enhanced machine learning is an upcoming subfield in machine learning and deep learning that aims to integrate known physical understanding of phenomena in the machine learning framework. On a side note, if any of you are interested to share your work in any of our upcoming seminars, please feel free and do get in touch with us, with either myself, Andrea, or David, who is today not present. As for the format of this seminar, our speaker today will talk for around 40 to 45 minutes, followed by a Q&A, which you may do so either through the chat or by unmuting yourself and asking in person. So without further ado, I'll ask my colleague Andrea to introduce our speaker for today. And with that, I thank you all.
Oh, thank you, Zach. So Jinlong, our speaker today, is a research scientist at Caltech working with Prof. Andrew Stewart and Prof. Fabio Schneider on a data-driven climate modeling project. His current research mainly focuses on developing data-driven methods to learn stochastic or no-local closures for complex dynamical systems, like multi-scale, multi-physics, and chaotic, from direct and indirect data. Jinlong got his PhD degree in aerospace engineering at Virginia Tech in 2018. His PhD advisor is Prof. Eng Xiao, and his dissertation is about using Bayesian inference and physics-informed machine learning in turbulence modeling. So thank you, Jinlong, for joining us today, and the floor is yours.
Thanks, Andrea, for the introduction and for the invitation. So hi, everyone. Today, I'm going to share some recent progress about data-driven closure modeling using derivative-free Kalman methods. So the general motivation is to improve the prediction or modeling of the complex dynamical systems, which often involve multi-scale or multi-physics processes. And just because that we cannot afford to numerically resolve every details of those systems, and that's why closure models are usually needed to model some unresolved processes. And so for this talk, I will try to share some recent progress about how to improve closure modeling for complex dynamical systems using data-driven methods, specifically using derivative-free data-driven methods. So to briefly introduce the closure problem, let's imagine that we have a dynamical system in general form. And in many applications, we cannot afford to use numerical simulations to simulate every detail of the original state, the small u. And a common practice is to introduce some reduced order state, such as using cost-graining, principal component analysis, or more recently using autoencoders. And after choosing the specific reduced order state, capital U, we can also derive governing equation for the reduced order state, the capital U. But the problem is that just because the original dynamics is often nonlinear, and the governing equation on the dynamics for the reduced order state will not only depend on the reduced order state capital U itself, but also depend on some unresolved information carried by the original state, small u. So in order to close the system for numerical simulation, it is common to introduce approximation f tilde, and we hope that f tilde only depends on the reduced order state capital U, but can well approximate the true dynamics of the reduced order state, the F bar. However, we know that in many applications, the traditional model for F tilde usually not good enough, especially for systems with multi-scales or multi-physics without a clear scale separation. And that's why in recent years, people try to quantify the difference between F bar and F tilde with an additional term, M here, we call it model error term or structural error term. And people want to calibrate or learn this term from some type of data. So a straightforward choice of the data is what we call direct data. For example, we can get the true values of the reduced order state, capital U. And then we can just calculate post-processing the true values or evaluation of the error model term M by either using the difference between time derivative and the F tilde, or by definition, by calculating the difference between F bar and F tilde. So by using either approach, we can get data pairs of U dagger, the true reduced order state, and also the evaluation of M U dagger. But both approach of getting direct data may have some problems in practice. For example, the real data may be noisy or sparse, which means that the time derivative term here is difficult to obtain accurately. On the other hand, resolved information may not be available for real-world applications, which means that if we want to directly calculate F bar and F tilde, we may not have access to the small U dagger, the original state, which means that we cannot directly evaluate F bar to calculate the data pairs. So alternatively, we can also rely upon what we call indirect data. So for indirect data, in general notation, we just assume that we can have some data of the reduced order state U dagger. And also we have a kind of observation operator that operate upon U dagger. This observation operator can be, for example, the sparse observation of U dagger, or alternatively, we can use time average statistics of U dagger. But for indirect data, we just have some kind of indirect information about the true model error term M. And this talk will focus on the use of indirect data in this form. For example, sparse observation of U dagger or time average statistics of U dagger. Just use this type of data and try to learn the unknown parameters that help us parameterize the error model term by using Kalman inversion. Okay, so here I briefly introduce the formula of ensemble Kalman inversion, which is the specific common methods we use in this work. So the inverse problem in general form is presented at the top of this slide that we want to solve. So assume that we have unknown parameters theta, and we have a known format that bring us from theta to data space. And eta here just denote some noise associated with the way we obtain or calculate the data Y. And we assume that it follows Gaussian distribution unbiased. And for the EKI updating formula, is presented in the middle of the slide. The J here denotes the index of ensemble, and M represents the index of EKI step. So this updating formula can be understood intuitively in such a way that at the J's EKI step, we have current estimation of unknown parameters data. But we can also, in data space, calculate the mismatch in data space. And then after calculating the mismatch, we can use the covariance matrix in data space, try to normalize the mismatch in data space. Here, capital C denotes the covariance matrix. And after we get the normalized mismatch in data space, we can also use the covariance matrix between the data space and parameter space, try to project the normalized mismatch back to the parameter space. And we use the projected mismatch to update the current estimation of unknown parameters data. And then we get the next EKI step estimation about unknown parameters data. And we can do this updating iteratively until statistical convergence is achieved for the estimation of unknown parameters data. So there are several advantages of using EKI. The first one is that is a gradient-free optimization method. Which I will come back later for this point. Okay. So one of the example that we started before is turbulence modeling. So the turbulence is ubiquitous in natural and industrial flows, such as the examples that we presented at the bottom. And for turbulence modeling, Reynolds average Navier-Stokes Rens models are still widely used in turbulence simulations, even though they have limited predictive capability for complex flows. So to take a closer look at the Rens modeling, we can see that the Rens equation is presented in this slide, and the only unknown term is at velocity field. We try to learn the full field of what we call Reynolds stress discrepancy delta tau, the difference between true Reynolds stress and Rens model Reynolds stress. Okay. So before getting to more detailed results, let's briefly take a look at the pipeline of the Bayesian inference algorithm that we use. So first, we assume that we have access to some physics-based prior distributions. And then from that, we can sample delta tau, the Reynolds stress discrepancy. And then we have ensemble of initial states of delta tau. And then with the forward model, we can plug in the sampled Reynolds stress discrepancy delta tau and solve for the corresponding velocity field. And then we can get pairs of ensemble propagated states that we have the solved velocity, capital U, corresponds to the specific sampled stress distribution delta tau. And then we can compare the solved velocity with the observation data that we have. And then based on this comparison, we can use Bayesian updating, try to update the ensemble states. And then we have the updated estimation of the delta tau term. And then we can plug this term back into the forward model to solve for velocity again. And then we compare it with the observation data. So we do this pipeline iteratively until statistically convergence is achieved for the estimation of ensemble of delta tau. So in general, this Bayesian inference algorithm can be understood as kind of approximated Bayesian inference that we want to get the posterior distribution of delta tau that condition on some sparse observation of velocity, and we know that it's proportional to what we call likelihood function, and also the prior distribution of the renal stress distribution delta tau. So until now, although I already introduced the Bayesian inference algorithm, the whole pipeline, but there is still something is unclear. More specifically, is you might curious about how we get the physics-based prior distribution. So how we get the kind of the start point of this inference algorithm. So in this work, for the prior distribution of delta tau, we try to model it as a Gaussian process by using the standard square exponential kernel. And sigma here is what we call the field of variance. And the prior knowledge is used to specify the field of variance, which means that for the regions that we know that variance models usually does not perform well, we will assign larger values of the variance sigma. For example, we know that for this type of flow, we have recirculation regions here, and we have free shear layer regions here. For both regions, the variance models would not perform very well, and we assign larger values for the sigma field. And then we can use Calhoun-Love expansion, try to get the basis functions that can help us further reconstruct the renal stress distribution delta tau term. So for those who are not familiar with this method, you can think it's just eigenfunctions of the previous field of variance sigma, or essentially the eigenfunctions of the covariance matrix of the Gaussian process. And then with all these basis functions, we can further reconstruct the unknown term, the full field renal stress distribution, by just using linear combination of all these basis functions. And then the unknowns becomes the coefficients of linear combination of all these basis functions. And the task of this work becomes to estimate those coefficients by using the Bayesian inference algorithm that we introduced before. So to summarize about the methodology part, we try to parameterize this renal stress distribution term by using the linear combination of basis functions we'll get from the physics informed prior of the delta tau, and the unknowns become to the parameters that help us get the reconstruction of delta tau. And with sparse observation data of velocity field U, we want to estimate the posterior distribution of unknown parameters conditioned on the sparse observation. And with this posterior distribution, we can further reconstruct the Reynolds stress distribution delta tau. Okay. So after introducing the general methodology of this work, let's take a look at the performance of this method. So in this slide, I present both the prior and posterior results for the soft velocities at several vertical profiles. And here, the red lines represent the baseline range results. And the other gray lines represent the ensemble of simulation that we incorporate the sampled Reynolds stress distribution delta tau. And the blue lines here represent the ensemble mean. The solid black line here is the direct numerical simulation data, which we view as the truth. And for all the black crosses indicate the location that we have observation of velocity. As we can see that after we sample from the prior distribution of delta tau and try to use those samples to solve the corresponding velocity, the gray lines here tends to scatter around the baseline range result. And just because the prior, we use zero mean prior for the Reynolds stress distribution, although the mapping from delta tau to velocity is nonlinear, but still for the propagated velocity by using the samples from the prior distribution of Reynolds stress distribution, we can see that the ensemble mean still stick very close to the baseline range results. But after we incorporate the information carried by the sparse observation of velocity at black crosses, we can see that the posterior distribution of velocity field tend to have a much better agreement with the DNS truth, especially for the region with recirculation. Okay, so this comparison indicates the improvement of the results by incorporating sparse indirect velocity data when we try to learn the full field Reynolds stress distribution term. Okay. And for some of you, already noticed that up to now, the error model term, we made an assumption that is a function of spatial coordinates. And it can also be generalized to the function of state variable, capital U. And for those who are interested in this kind of generalization, there is a very recent paper from my colleague Jinlong Zhang and my previous PhD advisor, Han Xiao. And I present the link, the archive link of this paper. And for those who are interested in such kind of generalization, I highly recommend to check out this paper. Okay. So for the second part of this talk, I will try to illustrate another scenario that for some applications, we might not have a good existing model of F tilde. So in that case, the error model term becomes to the term that help us characterize the dynamics of the reduced order state, such that the n term here tried to approximate the whole term bar. And just because in the situation that we are using indirect data, we usually don't have a lot of data to help us calibrate the term m here. And in order to avoid overfitting, we also incorporate sparse learning into the previously introduced learning algorithm, try to help us avoid the possibility of overfitting. And that get us back to the one of the advantage of EKI that I briefly mentioned before, that the core task of EKI is equivalent to a convex optimization problem. So to further illustrate this point, we can view ensemble coming inversion EKI in such a way that if we introduce a new variable W equals to the evaluation of the foreign model, and then we can augment the unknown parameters theta with this new variable. And then we can formulate a noisy observed dynamical system in the kind of the form presented in the middle of the slide. And the updating formula of ensemble common inversion can be viewed as applying standard common filter to this noisy observed dynamical system. And also, just because we can view the updating formula of ensemble common inversion as applying standard common filter to this noisy observed dynamical system, actually is also equivalent to solving the optimization problem presented at the bottom. So this optimization goal can be understood intuitively such that we want to find a vector augmented vector V that not only give us a good agreement in data space, but also it's not very far away from the forward evaluation G theta. And as we can see here, after formulating the optimization goal explicitly, we can see that for each EKI updating step, the equivalent optimization problem is actually convex with respect to the augmented state V. And if we rewrite the optimization object a little bit, we can get the more standard quadratic programming form of the objective function of standard EKI for the updating formula for each EKI step. And then imposing sparsity within EKI can be done, just try to incorporate an L1 penalty or constraint to this standard quadratic programming problem. However, up to now, we still have a remaining problem that the L1 penalty inequality constraint is not linear inequality constraint, which means that we still need to do a little bit more work to be able to use standard quadratic programming package to solve this problem. So in order to achieve that, we grab inspiration from the paper from Professor Turing. So for those who are familiar with this method, it's also known as lasso. And we introduce auxiliary variables, V plus and V minus. And with these two auxiliary variables, we can replace the original variable v in this optimization problem. And by doing so, we can get the standard quadratic programming problem with linear inequality constraint with respect to the auxiliary variables v plus and v minus. So for the final form of the optimization problem, we can directly use standard quadratic programming package to solve it. So after introducing the methodology part of the sparse EKI, let's take a look at some results. So we try to test the performance of sparse EKI using a dynamical system, what we call Kalman-stochastic equation. And for the true KS equation is presented at the top. And for the model system, we assume that we don't know the dynamics of the KS equation. And we try to mimic this dynamics with some linear combination of different orders of derivatives of U. And more specifically, we try to incorporate both linear and nonlinear terms up to the fifth order derivative of U. And the parameters alpha j and beta j here are unknown to us. And the general goal is try to use some time average statistics of U, the state variable, and trying to learn the unknown parameters alpha j and beta j. And here we present the results in data space. So the time average statistics we use are some moments of U and also autocorrelation of U and spatial correlation of U. And the results correspond to the sparse EKI, but for the standard EKI, it achieves similar agreement with the true time average statistics in data space. But when we try to simulate the calibrative system by using standard EKI and sparse EKI, we can see that the dynamics of standard EKI show a noticeable difference from the true system, but the sparse EKI tend to give us a much better agreement with the true system. And here we present the results of the L1 norm of all the redundant coefficients, because we know that we only have sparse terms in the true KS equation, which means that for most of the unknown parameters, alpha j and beta j, they should be 0. And we present the L1 norm of all the redundant coefficients for the sparse EKI. And we can see that by incorporating sparsity, even just we use some time average statistics of U, we are able to push all the redundant coefficients to values very close to 0, which help us overfitting in the data space. So for those who are interested in some more details of this work, I listed a paper that related to this topic at the bottom. Okay. So for the last part of this talk, I'm going to share some recent progress about going beyond deterministic closures. So for the previous results that we showed, we only focused on trying to learn a deterministic alt model term M. And for the rest of this talk, I will try to show some results about not only incorporate a deterministic model error term, but also try to incorporate a stochastic term. So for the deterministic error model term, and also for the diffusion coefficient of the stochastic term, as both of them are functions, unknown functions, we can parameterize them either by using dictionary learning, Gaussian process, or neural network. And for the W dot here, it just denotes the standard Wiener process. And after we choose the specific form of parameterization, M and sigma, so the remaining unknown thing is just the unknown parameter theta that carries the unknown parameter alpha of the M term and unknown parameters gamma of the diffusion coefficients. And the general goal, similar to the previous two parts, we try to estimate the unknown parameters theta from some indirect data y, such as time average statistics of the state variable capital U using ensemble conversion. Okay, so for the toy example we started for this method, we used the noisy Lorentz 63 system. So for the true system, it's just the standard Lorentz 63 system plus some noise. And for the model system, we assume that we don't know the constant diffusion coefficient, and we also don't know a linear term within the standard Lorentz 63 system. And we try to learn both unknown parts by using indirect data. And in this case, we only use moments of state variables up to the second order. And here we show the comparison of the calibrated system and the true system in data space. And for the left figure, it shows the result using stochastic term. And for the right figure, it shows the results by incorporating the stochastic term. We can see we achieve good agreement in data space for both results. But we ask ourselves a question: does it mean the two models are good? In order to answer this question, we try to simulate the model system for a much longer time and try to plot the invariant measures. So for those who are not familiar with the terminology here, you can think it's just the probability density function of state variables when we simulate the system for a very long time. And as we can see here, for the model system without stochastic term, the invariant measures show noticeable difference from the true system. But if we incorporate the stochastic term and also try to learn it, we can see that we achieve much better agreement with the true system. But I have to say that this is just a toy example, which means that the true system, we design it such that it carries the stochastic term in the similar form as the model system with stochastic term. So in order to further test the performance of this method, we try to study another Lorentz 63 system, which was studied by Professor Tim Palmer about 2 decades ago. So for the true system, we try to write the Lorentz 63 system in POD transformed coordinates such that the third dimension carry least energy. So in this example, it carries only about 5% of total energy of the original system. So just because that for the third dimension, it carries a tiny amount of energy of the true system, a straightforward way to build a reduced order model is just let's discard the third dimension and only simulate the other 2 dimensions, the more important dimensions. the Professor Tim Palmer found that if we completely remove the third dimension in this POD coordinates for the reduced order system, it will lose the chaotic behavior completely. And more interestingly, if we just add some very simple stochastic term in the original work, it's just white noise, and we are able to get the chaotic behavior back, at least qualitatively. So inspired by this work, we tried to play with the same system using our data-driven stochastic modeling framework, try to add both deterministic part and stochastic part to the reduced order model. And we try to learn the unknown parameters of M1, sigma 1, M2, sigma 2 by using time average statistics of state variables A1 and A2. So here I present the key results of this test case at the bottom. So as we can see that for the invariant measure of A1 and A2, the model system show a good agreement with the true system, which means that if we incorporate the unknown deterministic term and stochastic term and try to learn them from data, we are able to get more quantitative agreement with the true system compared to just adding the very simple stochastic term using white noise. Okay. So to summarize, many complex dynamical systems involve multi-scale dynamics without a clear separation of scales, for which numerically resolving all the scales is too expensive and closure modeling is needed when simulating those systems. And we demonstrate the learning of closures based on indirect data, such as sparse observations of system state, or some time average statistics using ensemble Kalman inversion. And we also show that sparsity constraint can help avoid overfitting in the learning of closure models when only indirect data is available and the amount of data is limited. And also, we show that derivative-free Kalman inversion methods enable learning of stochastic closures using indirect data. So with that, I'm happy to take any question. Thank you.
Thank you so much, Jinlong. Thanks for your thorough presentation and for sharing your work with us. We have a question from Dennis. Dennis, would you like to ask? Yeah.
Can you hear me?
Yeah.
All right. I just wonder about this. What is this time average statistics? Like, sorry if I missed it. In the previous slide, you had this, if you can go back to this KS equation slide.
Yeah. Let me try to get that. Not sure why I cannot.
Maybe I should
move around slides. Maybe
you do it now, I guess.
Let me try to stop share and share again.
Yeah. Yes.
Okay. Yeah. Can you see my slides?
Yes.
Yes.
Great. So if I understand correctly, so your question is about the specific form of time average statistics.
Yeah, you had one slide with the pictures. I think that would be clear there.
Yeah. So let me get to this one. Yeah.
Yes. Also, maybe the later one. Okay. Data is maybe like just the next slide.
Yeah, for the next slide,
Are you observing like this? I guess if the x-axis is time, somehow the horizontal sums or something.
yeah, you can think in this way. So for the first moment, it's just the horizontal mean. You can think because horizontal axis is time. So for the first moment of state variables, it's just the horizontal mean.
Okay.
And we also incorporate high order moments. And in this test case, we also incorporate autocorrelation, which tells us some information about the kind of the temporal memory effect and the spatial correlation.
Yeah, thank you.
Thanks, Dennis. Do we have any other questions?
So maybe I can ask a question. So if you can go to the preceding slide, so the one, yeah, should be. So okay, I think I missed this during the presentation, but can you expand a bit more between the difference between the AKI and the standard QCQP approach?
So for the EKI, we have the standard updating formula in stage 1 that we presented in the middle. So that's kind of the standard updating formula that we just use this updating formula iteratively to get the results of final estimation of data. But in some previous works of EKI, the researchers have shown that it is equivalent to applying standard common filter to this noisy observed dynamical system, which means that for that updating formula for each EKI step, it is equivalent to solving this optimization problem with the augmented state V here as the unknown. As I mentioned, that this kind of link can be understood intuitively because for this optimization problem, we generally have two kind of objectives. The one is try to get the kind of the G theta evaluation that is close to the data Y. And we also want to have kind of, because for this updating formula, if we solve this optimization problem, the V is unknown. So for the per se here, we have already evaluation of G theta, which means that we don't want to modify the current evaluation of G theta a lot, but we still want to have a closer agreement with data. It's kind of this trade-off that we made in this optimization problem. But in summary, this optimization problem you can think is the equivalent form of solving or applying the EKI updating formula, which means that if we don't use that updating formula, but solve this optimization problem for each EKI step, we will get, ideally, we will get consistent results. But the reason that we introduce this optimization problem is that we want to further incorporate some constraints. So, which means that we don't solve this standard optimization problem because it's equivalent to EKI updating formula. So for each EKI step, we use that standard updating formula to get the estimation of current step, but we solve an additional optimization problem that adding the L1 penalty constraint to this standard optimization problem. You can think that after standard EKI updating, we just slightly modify the estimation to promote the sparse solution.
Okay, thank you.
Thanks for the question.
Thank you, Jinlong. Do we have any other questions? Unfortunately, I need to vacate the meeting room I'm currently in. I was asked to leave. But before I do, just maybe. All right, I guess we'll wrap this up here. Thanks again, Jinlong. Round of applause to you.
Thank you. Thanks a lot.
For the invitation and for all the questions. Thanks.
It's a pleasure. For the rest of you who are still in the room, stay tuned for our future talks by logging into our website. Thanks again, and good day to all. Bye.
Thanks. Bye.